everyone, and thank you for that great introduction. I'm so excited to speak with you today on the topic of evaluating synthetic data with post-processing techniques. So to get started, I would like to first go over the outline of what we'll discuss today. So we'll first start by understanding what is the AI data problem. Then I'll cover some synthetic data examples to help you understand what exactly is synthetic data. Then we will talk about the data generation workflow. Then we'll cover the post-processing techniques, namely 3, which are dataset analytics, domain adaptation, and Umap. And we'll have some time at the end for Q&A. So starting with, what is the AI data problem? On the left, so we believe it has these 4 quadrants, and on the left are issues related to cost and time to market. And on the right are issues related to performance. So with cost and time, real data is expensive, unavailable, or impossible to acquire and label. And this blocks innovation because without data, it's impossible to explore new sensors and data types. And on the right, issues related to performance. I'm sure all data scientists are aware of the issue of bias. So certain rare objects, rare scenarios can be hard to capture, and real data just can't provide those. And that leads to bias in the AI model. There's also the issue of accuracy with your data. So data labeling can be imprecise and incomplete, and this can lead to less accurate AI models as well. So synthetic data solves the AI data problem. Synthetic data is engineered data that the AI interprets as real data. And when I speak about synthetic data, it can come in all forms. It could be text, sounds, images, videos, but for our particular use case and for this entire presentation, we focus on computer vision use cases. On the right is one example of a synthetic data image. This is an aerial view of like a cityscape. You could see buildings, the tops of buildings. You could see there's 2 crane trucks over there. You could see there's shadows. It's a daytime type of situation. So this is one example. I'll cover more examples in the next slide. Gartner said in September 2021 that 60% of data used for AI and data analytics projects will be synthetic. And by 2030, synthetic data will have completely overtaken real data in AI models. And Forbes said in July 2022, imagine if it were possible to produce infinite amounts of the world's most valuable resource cheaply and quickly. This is a reality today. It's called synthetic data. So synthetic data fills the gaps that real data cannot. So I wanted to share the variety of synthetic data examples because you can have synthetic data in virtually any domain. We have generated synthetic data through various different simulation engines. So here you see images that we created with Blender, Omniverse, Quadradocs, our homegrown SAR simulator, and there's also various sensors that can be modeled. So the basic RGB sensor, hyper, multispectral, infrared, X-ray, MWare. So I want to dive into a little bit more detail on what all of these images were created for. So on the top left is our 2 examples of satellite and aerial imagery, similar to the example before. So you see example of 3D and 2D backgrounds. One is kind of from the top looking down, and the other image is an aerial view. And this was created for the Ensign Challenge. So Ensign stands for National Security Innovation Network, and the goal for these data sets was detecting air conditioners on rooftops. So you can kind of see where the air conditioners are here. On the top right are some examples related to different security applications. You can see one of the images is similar to what you would see as a Ring video capture of someone's front porch. This is security for home security. And we have 2 GIFs here. This is a desert scape and an RGB sensor and an MWare sensor. MWare stands for medium wave infrared. They were both mounted on a platform together, and this was simulating coincident collection of a dust storm. And you can see there's people in both of them. You see there's maybe some deer, and the goal was to have the humans and animals obstructed by the dust storm. And you can see it does successfully do that. On the bottom left are some applications related to X-ray and medical use cases. So one of the images is baggage scan example. So this is what you would see at baggage scans in the airport. You see one of these bags, it has things like glasses, keys, shoes, and maybe a knife. So this is obviously detecting forbidden objects. This was with the X-ray sensor and using the Quadradox simulator. We also have an example of microscopy used for IVF, where a microscope is coming into focus. And on the right, we have some non-visible sensor type examples. So synthetic aperture radar, or SAR, is used to detect ships from satellites, and SAR works by not being obstructed by clouds, so it's a useful technology. And this SAR simulator is our homegrown simulator. And we also have an example of hyperspectral and multispectral imagery of the city over there as well. So now that you've seen various domains and examples of synthetic data, I wanted to share with you a piece of research we did with Orbital Insight. This was a small business innovation research grant that we worked with Orbital Insight for, and the goal was to search for cranes and crane trucks as an economic indicator in satellite imagery. So these two objects, cranes and crane trucks, were rare relative to other features in overhead imagery. So it meant that they would have to run really large labeling campaigns to collect those examples, which was really not possible. And what they had was an original data set with just 100 examples of each of these classes. And what we did was we filled the gaps with synthetic data. And you can see on the bottom left, there's 6 images, and these are all mixed with real and synthetic. It's really hard to tell which is synthetic and which is real. And we were able to supply several thousand more examples of each class. And we were able to increase the precision scores of the model. So on the right, you can see a graph that shows that the combined synthetic and real data led to 2 to 3 times improvement in AP scores with the peak performance. So clearly synthetic data helped. And one large issue with real data here was that the objects were difficult to label because the images were pretty big and the objects were very small. There was inconsistent sizing of crane bounding boxes, and also similarities between crane trucks and cement pumps was another notable challenge. So synthetic data was able to fill this gap, and because synthetic data is simulated, it's able to give you the pixel perfect accuracy in your dataset annotations. And so you know exactly where everything is because you've built that simulator. So now that you've seen examples of synthetic data, you know that it's useful, you would assume that this is the workflow that's required to use the data and train an AI model. You think all you need is a simulator, you get your data set, then you can just feed it into your AI model, train it, and then you're done. You got your AI model, it's ready to go. But what we found is in the real world, that's not the case. The real world workflow has more steps associated with getting an AI model, starting with asset acquisition. So you have to understand what's the domain that you're trying to simulate. Which sensor would you need to use? Which simulation engine do you want to work with? Once you've decided all of those things, you can begin the world building process. So that means putting all of your assets together, whether that's your 3D models or your backgrounds. This includes writing your physics modeling scripts with your simulator and your engine. Then you get a working simulator, but you need to be able to run that simulator with a large amount of managed compute. You need really powerful GPUs to get your data sets. And then once you get your data sets, you want to be able to understand at a high level what's in your data set. Is the data set going to be useful? Is it modeling the things that you would like to see as what your real data needs? And then you can use that in your AI model and train it. And oftentimes your data will miss certain things. So you're gonna be working in a cyclical process to keep fine-tuning your simulator, maybe introducing more 3D models and more variation in your background. So this is a cyclical process, and we found that a synthetic data engineer must work with the data scientist together to build the right data. And now I would like to focus on the two highlighted steps in this workflow, namely post-processing and the quality assessment steps. So here we'll shift to talking about the post-processing techniques. The first post-processing technique is dataset analytics. And this technique is a way to do a quality assessment of your dataset at a high level. So this is essentially getting statistics about what's in your data. While there's many statistics you could obtain, we found that there are three that are the most useful. The first one is the properties of a data set. So this is understanding high-level metrics of the data set, such as distribution of image sizes and formats. And the second one is object metrics, so understanding your metrics of object classes and understanding more distributions of bounding box sizes. So with object metrics, you can understand if you have maybe too many objects of one class or too little objects of another class. You can understand if you have enough variation of sizes of objects in your data. The third one is mean brightness. So from our perspective, we will output a histogram of the average brightness where each image contributes a count. And this is a pixel level metric that informs the lighting of your simulator or your data set. This is useful for cases where if you want consistent lighting across each of your images, maybe you're doing a monitoring of like an indoor warehouse where the lights are always on, you'd probably want consistent brightness for each image. Whereas if you're trying to simulate different times of day, then you would want to see different variation in your brightness. So I have some screenshots here of two plots that we provide. This is just code that we've written, and we get charts of like, for example, a heat map of the size of bounding boxes and object aspect ratio density, and these are pretty general, but what I want to point out is that when you just look at a chart like this, if you don't know the domain and you're not the domain expert, you are not going to know how to interpret that chart. So each data set is very unique and each domain is unique. So only that domain expert will be able to tell what they're looking for and if that data set is going to work for them. And all we can do is provide the tools for the data scientist. So this is an evaluation technique, but I want to move on to talk about another technique that is related to post-processing, and this is more for introducing variation in your data sets. So this is domain adaptation using CycleGAN. CycleGAN is Cycle Generative Adversarial Network. This is a deep transfer learning application for image-to-image translation, and it does not require paired examples. So for this technique, a pre-trained based GAN model is applied from a source to target image. You can see a really great example here on the bottom left with the horse being transfigured into a zebra. Things to point out here are that the stripes are only applied to the horse. So the image that's on the left, or sorry, the video on the right, that's not really a zebra, that is actual transfer of the stripes. And the stripes are only transferred to the horse. The grass and the trees in the background all stay the same, although you do see a little bit of the post, sometimes getting the stripes as well. So this was research done in 2017. So the writers of this research, they have a open source GitHub called CycleGAN that is available. This is an open source library, and you can use it to transform your data sets as well. And the biggest thing to understand with CycleGAN is, I've quoted here, CycleGAN, as well as any GAN-based method, is fundamentally hallucinating part of the content it creates. So you have to understand when to use CycleGAN, because you may not get the right transfer if you're using it for certain use cases. So the biggest transfer cases that this is useful for are season transfer, styles, transfiguration, filters. So maybe you want to sharpen an image. I have an example here on the right where we converted a basket of apples and oranges to just oranges. We used a pre-trained model called Apples to Oranges from the Berkeley website linked below. This model, for example, you could see this basket, and there's maybe 8 apples and 4 oranges, and on the right, all of the oranges stayed the same. Maybe they got a little bit darker shade of orange, but all the apples did successfully get turned to oranges. So this is an example of transfiguration as well. I wanted to share more examples of domain adaptation with CycleGAN. On the left, we have an example toy box simulation. And the physics for this is just to drop toys into a box. There's all kinds of different toys here. In the middle, you could see that we use the Van Gogh CycleGAN model, and it is definitely turned into the style of the great painter Van Gogh. And on the rightmost is the style transfer for the style of painter Cézanne. And one thing to note is every object is in the same location as that original synthetic image. The only things that have changed are just the styling. So this is a way to introduce variability in your data set, and I wanted to share a study that we did. So domain adaptation with plus synthetic data and the results that we got out of this project. So this project was done for the Open Geospatial Consortium. This was the ODSC Testbed 19 project. So what I want to point out is the images we used. So some sample images are on the top. On the left is the original simulated synthetic image. This was the use case of planes on the tarmac. The middle image just has a variation of color and scale of assets, and sun angle of the scene are varied. And on the right is the same image as the one on the leftmost, but it has been modified with GAN-based domain adaptation. And here we use the XView model to transform it. And I want to talk about the performance of using domain adaptation with synthetic data. You can see on the chart below that the basic with GAN was performing the best out of all of the other combinations in terms of model training. And this was zero-shot training. So this zero-shot training approach means that the model has used no real examples of the target object in its training. It has only been fed with synthetic data. So basic with GAN performed the best out of all of them. One thing to note is that all combined approach was maybe the least accurate. We're still not sure why, but this was a really great study that we just recently did. So now that you've seen that domain adaptation and synthetic data combined leads to good results, I wanted to talk about the third post-processing technique, and this is called Umap. So Umap stands for Uniform Manifold Approximation and Projection, and this is a technique that lets you analyze images, word embeddings, point clouds, and sounds. You can use it to generate visualizations as well as transform new data into learned space for machine learning tasks. And this is another great open source tool that's out there. I've linked the docs here below. I wanted to give an overview of how dimension reduction looks like. So this GIF is Umap Zoo. This is a way to understand how 3D, when converted to 2D, what that looks like. And it's just reducing point clouds of animals. But Umap will reduce many dimensions into dimension you desire. For our particular use case, we are reducing to 3 dimensions. When we use Umap, we are comparing synthetic data to real data. On the bottom right is a really great GIF that shows how you can visualize Umap results. For this example, we have 3 separate unique data sets. One of them has original XView cropped images, another one has GAN adapted data set, and the third one is just simple RGB. And you can see that there's this 3D plot that you can interact with and see the clusters and outliers. And the goal is you can inspect every single image in this point and understand what kind of feature may have led to it being in that spot. So Umap identifies features on its own, and clusters and outliers found within the low dimensional space are representative of patterns found in the source data. So this allows data scientists to inspect if the right features are accurately represented within the data, and you can kind of play around with understanding which feature sizes will lead to certain points or clusters. The way that we're using Umap is we first start with the original image, then we run it through a neural network, then we run that through the Umap, which reduces it down to 3 dimensions, and then we get our feature comparison plot. So we have a really great blog here. If you want to learn more about how we're using Umap, you can read through that. And I also want to note that with these points, maybe you can inspect them further, and only the data scientist and domain expert would know what they're looking for as well. So there's not exactly like standards that we can give out for understanding that, the data, I mean. So that's all I've got for my presentation today. We covered the 3 different techniques of post-processing, 2 of which were for evaluating synthetic data, notably dataset analytics and Umap, and the 3rd, which is domain adaptation, for introducing variability in your dataset. And so with that, I'd like to open it up for Q&A. Is the QA of the synthetic data done manually or automatically? Yes, that's a really good question. So with dataset analytics, that is an automatic type of thing. On our platform, you can run like an analytics job, and that will let you understand the properties, and you can pick which analytics type you want to do. For Umap, that is a manual process. Most likely the data scientist is going to, look through each different feature sizes and, the 3D plot themselves. So that is a manual process.